Good morning, everyone. Thank you for joining us today. In our last deep dive, we kind of looked at the big picture, right? The grand architecture of modern computing, from the cloud all the way to the edge. Well, today, we're zooming in. We're getting our hands dirty with the revolutionary tools that actually bring that architecture to life. This is the how behind building modern software, the Cloud Native Toolkit. And this quote right here, it gets right to the heart of it. Cloud native isn't just about taking your old applications and dropping them into a new place. No way. It's a total paradigm shift. It's about building software that is designed from the ground up for the incredible scale, the resilience, and the constant change that the cloud makes possible. We're going to be exploring the trifecta of modern development: containers, Kubernetes, and serverless, all driven by this powerful philosophy of microservices. So here's our roadmap for today. We'll start with the cloud-native revolution. Then we'll dive deep into containers, Kubernetes, serverless, and finally, we'll talk about the microservices architecture that really ties them all together. Let's jump in. Okay, let's kick things off with containers. Now, to really appreciate why these things are so revolutionary, we need to understand a classic, deeply frustrating problem that plagued developers and operations teams for years and years. Ah, yes, the infamous "it works on my machine" problem. If you've been in tech for a while, you've felt this pain. A developer's code would run absolutely perfectly on their laptop with their specific setup, but then, the moment it was deployed to a production server, it would just crash and burn. So why did this happen? It was because of something called environmental drift. These tiny but critical differences in operating system patches, library versions, or config files, and this created a constant, painful battle between developers trying to ship new features and the operations teams whose job it was to keep everything stable. Honestly, it was a huge bottleneck on innovation. The solution was containerization, and it used this brilliantly simple analogy: the standard shipping container. Think about it. Before those big metal boxes, loading a ship was just customized chaos. But with a standard container, it doesn't matter if you're shipping bananas or car engines. The box is the same, and any crane or ship can handle it. Docker brought this exact idea to software. A container, as you see on the right, packages up the application and its entire environment, all the code, libraries, configurations, into one single standard unit. And the result? The environmental drift is eliminated, that friction between teams disappears, and "it works on my machine" finally becomes "it works everywhere." So to really see how this works, we need to quickly understand the difference between two core concepts: an image and a container. You can think of it like a class and an object in object-oriented programming, or maybe even simpler. Think of it as a recipe versus the cake you actually bake from it. Okay, so the workflow starts with a Docker file. This is just a simple text file. It's a blueprint with instructions like start from a base Linux OS, install Python, copy my app code, and run this command when you start. You run the Docker build command on this file, and that creates an image, which is a read-only static template. That's the recipe. Then when you run Docker run, you create a live running container from that image. That's the actual cake. And what's so amazing is that you can spin up hundreds or even thousands of identical, perfect containers from that one single image. Now, you might be thinking, hold on, didn't we already have a way to isolate applications with virtual machines? And you'd be absolutely right. But containers represent a massive leap forward in efficiency. And the reason all comes down to what they virtualize. See, a virtual machine virtualizes the underlying hardware. This means each VM needs its own complete separate guest operating system, its own kernel, its own system files, the whole shebang. That's why they are huge. We're talking gigabytes in size, and they can take minutes to boot up. A container, on the other hand, does something much cleverer. It virtualizes at the operating system level. It shares the kernel of the host machine it's running on. And this is the key. By not needing that full guest OS, containers are incredibly lightweight, megabytes instead of gigabytes, and they can start in seconds. This efficiency means you can pack far more containers onto a single server than you ever could with VMs, which has just huge implications for cost and resource utilization. This consistency and the lightweight nature of containers enables a profoundly powerful operational pattern, one that fundamentally changes how we think about our production environments. It's called immutable infrastructure. In the old world, to update software, you'd log into a running server and apply a patch. This was risky, and it inevitably led to configuration drift, where each server slowly became this unique, fragile snowflake. With immutable infrastructure, you never change a running container, ever. To update, you'd build a brand new image with the new code, You deploy new containers from it, and then you simply destroy the old ones. What this really means is your production environment stops being this precious, handcrafted thing and becomes a predictable, disposable commodity. This makes deployments incredibly reliable, and rolling back a bad change? It's as trivial as just redeploying the previous image. It's a total game changer for stability. So, containers solve the problem of packaging a single application reliably. Awesome. But what happens when modern systems are made up of not one, but hundreds of these containerized services all working together? Well, trying to manage that complexity by hand it's impossible. This created the need for a completely new kind of tool, a container orchestrator. So what exactly is orchestration? Well, if each container is a musician in an orchestra, the orchestrator is the conductor. It's the intelligence that automates the deployment, the scaling, the networking, and the health management of countless containers across a whole fleet of machines. It makes sure the entire distributed application works together in perfect harmony. Now, while a few orchestrators popped up, one project born inside Google and now an open source giant became the undisputed industry standard, Kubernetes. Its power and its popularity really stem from a core operational principle that feels almost like magic, providing a level of automation and resilience that was previously unimaginable. And here it is. The magic of Kubernetes is something called desired state reconciliation. See, instead of giving Kubernetes a series of commands on how to do something, you simply provide a declaration of the state you want. You write a configuration file that says, for example, I want 3 replicas of my web server running this container image. You hand that to Kubernetes, and from that point on, Kubernetes' job is to constantly watch the system and work tirelessly to make reality match your declaration. If a server dies and a container vanishes, Kubernetes sees the mismatch. Current state is 2, desired state is 3, and it automatically schedules a new one on a healthy machine to fix it. It is a relentlessly self-healing system. To work with this system, you just need to know a few key building blocks. The cluster is the collection of all your machines, or what we call nodes. The smallest thing you can deploy isn't a container directly, but a pod, which is basically a logical wrapper that holds one or more tightly coupled containers. You manage these pods using a deployment, and that's where you declare your desired state, like I want 3 of these pods. And finally, since pods can be created and destroyed constantly, they need a stable network address. And that's the job of a service, which gives you a single, reliable endpoint so other parts of your application know how to find them. And this isn't just theory. Just look at Spotify. Their entire backend is composed of hundreds of individual services, all built and managed by dozens of autonomous teams. Kubernetes is the unified platform that makes all of this possible, allowing each team to deploy and scale their part of the system independently without breaking everything else. This is what fuels the rapid innovation we see as users. It really is the engine of modern digital agility at a massive scale. Containers and Kubernetes are absolutely incredible. But even with Kubernetes, you're still fundamentally managing a cluster of servers. Serverless computing takes the next logical step in abstraction and asks a really powerful question. What if developers didn't have to think about servers at all? Okay, now the name serverless is a little bit misleading because of course there are still servers. The key idea here is that the developer no longer has to provision them, manage them, patch them, or even think about them. All of that is handled by the cloud provider. And the most common way this model is implemented is called functions as a service, or FAS, with AWS Lambda being the prime example. With FAS, you write these small, single-purpose functions that are designed to run only in response to a specific trigger. As you can see here, that trigger could be an incoming HTTP request to an API, a new photo being uploaded to a storage bucket, a message appearing in a queue, or just a simple timer. When that event occurs, the platform handles everything. It finds compute resources, runs your code with the event data, and then tears it all down. You manage nothing but the code itself. This event-driven, totally hands-off approach offers 2 truly compelling advantages that fundamentally change both the operational and the economic models of computing. The first, and maybe the most dramatic benefit, is the cost model. With traditional servers, you pay for them 24/7, even when they're just sitting idle waiting for requests. It's a high fixed cost. With serverless, you pay only for the precise compute time your code is actually running, often metered down to the millisecond. If your function isn't running, you pay absolutely nothing. The second major benefit is automatic, elastic scaling. If 1,000,000 events happen all at once, the cloud platform will automatically run 1,000,000 concurrent instances of your function to handle the load with zero configuration from you. The New York Times has a fantastic real-world example of this. they used to maintain this whole fleet of servers that were running constantly, just waiting for journalists to upload photos that needed to be resized for the website. Most of the time, these servers were idle, but still costing money. They replaced this with a serverless workflow. So now, when a journalist uploads a photo to a storage bucket, that's the event, a Lambda function is automatically triggered. It resizes the image into every required format, and then it shuts down. They only pay for the few seconds of compute used per photo, saving an enormous amount of money and gaining infinite scalability for those breaking news events.
So we've covered the core technologies: containers for packaging, Kubernetes for management, and serverless for abstraction. These are all the how, but they're most powerful when they're applied to the architectural philosophy that drove their creation in the first place, and that's the why: microservices.
For decades, the dominant way to build software was the monolith. A monolithic application is built as a single, large, unified codebase. All of its functions are tightly coupled together and deployed as one single unit. And while this can be simple to start with, as the application grows, it becomes incredibly complex, slow to change, and really difficult to scale. Microservices offer the exact opposite approach.
A monolith, like you see on the left, is one giant application. So to change one small feature, you have to test and redeploy the entire thing, which is slow and incredibly risky. A microservices architecture, on the right, breaks that application down into a collection of small, independent services, each focused on a single business capability. So for an e-commerce site, you might have a user service, a product catalog service, and a payment service. Each one can be deployed independently, meaning the payments team can release an update dozens of times a day without affecting the product team. And each service can also be scaled independently, so if your product catalog gets tons of traffic, you can scale just that one service without touching the others. It enables team autonomy and incredible development velocity.
And this right here is where it all just snaps into place. Why did these tools become so dominant? Because they are the perfect match for this architecture. Containers provide the ideal way to package and isolate each individual microservice. And Kubernetes is the perfect platform to manage the staggering complexity of deploying, connecting, and ensuring the resilience of hundreds of these services all working together. The tools don't just support the architecture, they make it practical at scale. All right, we've covered the core of the cloud-native toolkit: containers for packaging, Kubernetes for orchestration, and serverless for abstraction, all in service of a microservices philosophy. So let's summarize the single most important takeaway from all of this. After exploring all these powerful tools and concepts, what is the one fundamental idea that you should really leave with about this shift in building software? Here's the key idea. Cloud native is so much more than just a location. It's an entirely new way of building and operating software. It's all about composing applications from small, independent pieces, packaging them consistently, and managing them dynamically with very high levels of automation. This toolkit is the engine of modern digital agility, empowering organizations to innovate faster, respond to change more effectively, and build the next generation of resilient, scalable applications. Now that we understand the tools, our next deep dive is going to explore applied innovation, cloud, and edge case studies to see how companies are actually using these concepts in the real world to solve some incredible challenges. I really hope you'll join us for that one. Thank you again for joining us for this explainer. To make sure you don't miss our next session, please be sure to subscribe to our channel, Tech AI and Beyond. We'll see you next time.